Hello, Chantelle. Remember last time we sit down together, we were talking about alkene addition reaction. As we work through the worksheet, we bump into a very unique phenomenon. And when we look at the textbook, or when we look at the note for an explanation, it was a one sentence explanation. And I don't know about you, I don't see any depth in that particular explanation, and I'm not satisfied. So I went on to do some research about it. And I have found some very fascinating explanation for that particular phenomenon. So I want to share them with you in this particular video. And I know you have a little bit difficulty when it comes to reading words. So my original plan was, Chantelle, writing out notes so you can have a read. Just to pass on the message to you in the form of notes. And I just realized maybe that wouldn't be the most efficient way to do it. Given that you might find it difficult to decode the words that I'm written, not to say that I don't have the best handwriting in the world. So I was thinking to myself, why don't we make a video about it? And here it is. So in this video, we will talk about that particular phenomenon that we encountered last time. And I hope by conveying the message in this fashion, it makes it easier for you to learn, and it makes you actually enjoy learning. Now, this particular phenomenon happens when an alkene group reacts with what we call a halide acid, which is a halogen bonded with a hydrogen. Halide means halogen. The acid bit just is being represented by the H, the hydrogen proton. So like hydrochloric acid, HCl. That's the halide acid. Right. So when an alkene group reacts with a halide acid, addition reaction could happen. The addition reaction will destroy the double bond in the alkene, and then both of the halogen and the hydrogen will be added into the carbon structure, forming one particular product. Right? Remember, addition forms one product, substitution forms two. Right. Now, when this addition happens, we were thinking, why would the halogen attach to the carbon with the least amount of hydrogen around it, rather than the other carbon? Now, in this case, it means, why would the halogen actually attach to this particular carbon instead of this one? Right, with the least amount of hydrogen. So this one got 2, this carbon has 2 hydrogen around it, and this carbon has 3. Why did that happen? Now the textbook says that was the explanation for the textbook, right? The hydrogen will attach to the carbon with the least amount of hydrogen, and that is actually a result or a phenomenon according to Markovnikov's rule. Now, Markovnikov must be a Russian guy, right? His name sounds Russian. Now, the first mechanism behind Markovnikov's rule is the cleavage of the halide acid. Now, the cleavage just means the split, right? We know all the halide acid is very polar. By polar, I mean the hydrogen itself it only has one proton in its nucleus, right? Because it's being the first atom on our periodic table. But on the other hand, the halogen is quite a massive atom compared to the hydrogen. So with more proton in its nucleus, now that generates a bigger attraction. So step 1 is the cleavage of the halide acid. Now in this case, we refer halide acids to any acid, with a hydrogen atom in there, bonded with any halogen. So for example, fluorine, chlorine, iodine, and bromine. So in the cleavage, the halide acid is broken down into a hydrogen atom, and hydrogen positive atom, and a halogen negative atom. In here, we referred the hydrogen positive atom as an electrophile. So any something that loves electron. Alright, so electrophile. Now that an electrophile is introduced into the system, it will target somewhere which is very electron rich, because it wants one, right? Electrophile. So this electrophile will target the double bond in alkene in an addition reaction. So once the electrophile has successfully broken down the double bond, or once the electron, the fancy word, delocalized in the double bond, it is freely to go to anywhere, right? It is free-flowing electrons. Now, there's two possible paths for all these free electrons to go. Path A, which is the majority of the electron from the double bond will move to the right hand side of the carbon, or path B, to the left hand side carbon of the double bond. Right? They got two paths to go. Now this is the crucial step, right? How do we know which path did the electron go? Now, to understand why the Russian scientist Markovnikov observed that the hydrogen will attach to the carbon with the most amount of hydrogen, while the halogen attached to the carbon with the least amount of hydrogen with it. To understand that concept, we must consider all the paths that the free-flowing electron will take, and then look at the outcome of all the paths and see, is there any reason why Markovnikov states that, that the phenomenon, that's what he observed is the correct, or is the final product. Right, if path A is taken, which means after the double bond is broken by the electrophile, hydrogen ion, in this case, the majority of the free-flowing electron will go to the carbon on the right-hand side of the double bond. Now, that would make that particular carbon more negative, right? Because it's all of a sudden, it has more electron around it, right? So that will make the whole carbon a bit more negative. On the other hand, the carbon on the left-hand side of the double bond will become more positive, right? Which makes sense. They were neutral when the double bond existed. But once the double bond is broken down, and if the majority of electron goes to the right-hand side, then obviously the left-hand side will become slightly positive, right? So after that happened, the electrophile, our hydrogen ion here, will attach to the carbon, which is more negative, right? Because it's got more electrons there. So this will give us a secondary carbocation intermediate. Now, the word intermediate is just to let you know that this particular molecule here is not the final product, right? It is just a molecule that was formed in the middle of the reaction, right? It is not the product. It usually, all intermediate usually exists in a higher energy state, meaning, to keep the intermediate alive or existed, it requires more energy. Right? So we have to constantly heating things up, which is not practical in an experiment context, because eventually the system would become stable at a particular energy level, and obviously the product of the experiment exists in a lower energy state compared to the intermediate. So eventually all the intermediate becomes the product, right? Because there's not enough energy to keep them as intermediate. Right. Now, the terminology here, carbo-cation, is very simple. Like carbo meaning got carbon in there, and a cation just meaning it is positively charged, right? So this intermediate contains carbon and it is positively charged, right? Now the secondary here, you know, the two with a little degree there, or second degree or secondary, meaning that means that this carbo-cation in the middle, right, with the charge in there, with the positive charge, is attached to two other carbon group, right? So if it's attached to one, it will be primary or first degree. If it's attached to two, it will be secondary, second degree. If it's attached to three, then it will be tertiary, right? Because it is attached to three, and it will be tertiary carbo-cation. So that's just the name, the meaning behind that particular naming. Right. If path B is taken, then everything happens in reverse, right? So all the free-flowing electrons will flow to the carbon on the left-hand side of the double bond, making it slightly negative compared to the carbon on the right-hand side of the double bond, which is now slightly positive, right? And then our electrophile will attach to the carbon, which is more negative. So on the carbon on the left-hand side of the double bond, forming this particular intermediate. Now, this particular intermediate is obviously called the primary or first degree carbo-cation intermediate. It is just because that the carbo-cation here got one carbon group attached to it, right? Hence it is primary or first degree, and that's what the name is, right? That's what happens. So these are the two possible outcomes, or two possible intermediate that this addition reaction can produce. Now, according to you know, once you get down to here, Chantelle, you can probably just go Google, right? Okay, then you will find out that secondary carbo-cation intermediate is more stable than primary carbo-cation intermediate. And from that, you can probably deduce that tertiary carbo-cation intermediate is more stable than secondary carbo-cation, right? So, there's not, just in case you're wondering as well, I don't think there's any fourth one, right? I don't think, because it has a hydrogen attached to it, right? Because the hydrogen have to go in somewhere. So I don't think you can attach to four carbon group. So there's no fourth degree, or what's the word for fourth? Quartic? All right. I don't think that exists, because you have to save a bond. You have to save an electron to bond with the hydrogen electrophile. So the order goes like tertiary. Oh, let me select that pen. So it goes tertiary is more stable. So more stable. Then secondary, and is more stable than primary carbo-cation intermediate. That means all the first, you know, in the result of a experiment, these two intermediate has a 50-50 proportion. right? So 50% of the intermediate will be a secondary carbocation, and 50% of the intermediate will be primary carbocation. But since we say that the secondary carbocation intermediate is more stable, that means they will remain secondary, right? While the primary carbocation intermediate is unstable, so it will break down itself again and forms, and then this process happens again. 50% of that will become secondary carbocation, and 50% of that will forms primary carbocation intermediates again. This process happens go on, and eventually, we're talking about, eventually, as time goes on, the primary product, or the primary intermediate, the only intermediate left inside the system, will be the secondary carbocation intermediate. Now, that is why the hydrogen attached to the carbon with the most amount of hydrogen, leaving that the halogen attached to the carbon with the least amount of hydrogen, right? That's the Markovnikov Rule. So that's it. That's the reason behind it. So now we come to the final step, step 3, which is just a step to show you what the final product is, right? The final product will have the halogen attached to the carbon with the least amount of hydrogen around it. That's it, right? So hopefully, Chantelle, now you understand why the Markovnikov Rule states, this would happen, and the mechanism behind it. Yes, normally this is where most people would stop, right? We come across a problem, we research into an answer, and once we find the answer, we are happy. But, Chantelle, a word of advice from me would be to fully understand something, right? We usually have to ask more than one why, right? So, according to some psychologists, usually, upon asking a question, you have to ask the subject 5 why before you get down to a meaningful answer from this, before you can get a meaningful answer from the subject. So we just asked one why, Chantelle. That was just one. Why the Markovnikov Rule is that way. So now I would, being a weird guy like me, being a nerd, being a geek, what do you call it, whatever you call it, I look into the second why. Alright, the second why now would be something called intermediate. Now, hopefully you were paying attention. No, I'm not doubting you. Hopefully you were paying attention just a couple minutes ago, I think, when we're talking about carbocation intermediate. Now, you just took my word for it, right? When I told you primary carbocation intermediate is unstable, and secondary carbocation intermediate is more stable than primary. So, but why? Why tertiary is more stable than secondary, and secondary more stable than primary? Right? And is there something less stable than primary carbocation intermediate? Right? So right now, we're going into this second why. So to understand the relationship behind primary, secondary, and tertiary carbocations, oh, this is such a hard word, carbocation intermediates, we first have to understand what intermediates is. Now, intermediates are high energy compounds that can be isolated but exist in a higher energy state than both the product and the reactant in the experiment. When we're talking about carbocation, obviously it is an intermediate that is most important in organic chemistry, since everything in organic chemistry contains, well, revolve around at least carbon, right? So carbocation is pretty crucial. Now, in my crude attempt to draw the 3D configuration of a carbocation intermediate, we can see that this is the carbocation that I'm talking about, this one, right? Because it's got an empty orbital, meaning it's just a bond that can be, well, a bond that can be used, right? So this carbon is more positive, right? This carbon is more positive because it is the carbocation intermediate. And it is unstable. All intermediates is unstable, but this carbocation can be stabilized by a phenomenon called hyperconjugation. Now, hyperconjugation is just another fancy word, scientists use, meaning it just means the overcrowded of electron, donating some of its negativity to its neighbor. That's what it means, right? It's just overcrowded electron donating some of their negativity to the neighbor carbocation. Right. For example, our the carbon group right next to the carbocation, in this case, this particular carbon here, the electron from this particular carbon group will donate some of its negativity to the carbocation right next to it. Now, this is called hyperconjugation. Electron density from neighbor sigma bond, which is single bond, can be shared to stabilize the empty orbital. Right? So, sigma bond, which is this one, the sigma bond, I should draw it clearly. Probably is this bond here, this dimension. So the dimension I'm trying to draw is the up and down, right? The up and down dimension. And then because the cross and the left, right, forward, backward is already full, the only empty orbital is the up and down one, the up and down. So electron density from the neighbor, this is the neighbor carbon group, from their sigma bonds can be shared, so some of its negativity is donated to stabilize the empty orbital. Right? So that's the reason behind why primary carbon is less stable. Because think about it, primary carbon-cation intermediate has one carbon group attached to the carbocation intermediate, right? So only one carbon group is donating some of its, very minor. It's only one carbon group is donating very, very minor amount of negativity to that empty orbital. But if we have two, right, more negativity can be donated to that empty orbital to keep it more stable, to make it become more stable than what its cell used to be. And not to mention, if you got three carbon group that's donating some of their negativity from around all the angles, right? Then it should be logical to say that tertiary carbocation intermediates will be the most stable, right? So that's the reason behind it. So hyperconjugation is the delocalization of charge by the interaction of an empty p orbital, the one that we just saw, with an adjacent ellipsed sigma bond. Now I know this is getting to very technical, the bond have to be adjacent and then ellipsed sigma bond. Don't worry about it. It's just meaning at the end it just means the more substitute the carbocation, the more stable it is, right? The more carbon group, or the more group that is attached to the carbocation, the more stable it is. Hence, that's why tertiary is more stable than secondary, is more stable than primary carbocation, right? Now let's have a look at the stability of the carbocation intermediates in ascending order, right? So now we start with the most unstable carbocation, which is the methyl carbocation, right? So it's the carbon with three other, attached to 3 electrons with, and then 1 empty orbital. So it is the most unstable one, and then the primary, the first degree carbocation intermediates with 1 R group. Now the R in this case would mean a functional group or a carbon group. Anything that has electron in it, right? Not just hydrogen. Anything that has more than 1 or 2 electrons, right? And then we have the secondary carbocation intermediate, which has 2 R groups attached to the carbocation, right? And after that, we have, let me fix this here. We have the allylic and benzylic. Now, the allylic and benzylic it's quite a funny structure, because they got a proper they are now you'll be asking, why are they more stable than the secondary carbocation ion, the carbocation intermediates? Now that has something to do with their resonating properties. Now by resonating, I mean this double bond can become, wrong color. Okay, this one. This double bond over here can rearrange itself and become this, right? Well, in fact, I think they on this side should be R as well. So, should be a function group as well. So it's like that. So it can resonate in 2 forms, right? Having the double bond on the left or having the double bond on the right. And benzylic, without, hopefully that a benzene, right, or the electron inside a benzene can delocalize. So a benzene ring, we can't find a definite structure for a benzene ring, because the benzene ring is constantly changing, right? So it will have this free structure depending on when we look at it, right? So it's like that. And then there's one last one, I think. Is it? Let me try to draw that. So you got here. Is it here? Oh no, got 2 structure then. Or more. Okay, so they can resonate. Right? So they can change from structure 1 to structure 2, or structure 2 back to structure 1. So this gives them more stability compared to the secondary carbocation intermediates. And now going to the most stable carbocation intermediate would be our tertiary. Our tertiary carbocation intermediate, which has 3 functional groups, or 3 groups with lots of electrons attached to the carbocation in the middle. Now, there's something funny, interesting that I found that you should that I want to share with you. If a carbocation can rearrange itself to increase its stability, it will. So remember the word unstable, meaning it will shatter and then reform, right? It wouldn't just shatter and stay shatter, right? As long as there's energy inside the system, it will become unstable and reform into something that is more stable. Now, stable in this case, in the chemical reactions, means that it requires a less energy to hold it together. So that's what that is what it means by stable. So the intermediate will keep breaking down itself to form, into different structure, and then until it reach a structure that requires the least amount of energy to hold it together. And after they reach that particular structure or that level of energy, it will just stay there, right? And there's no further need to break down because it is stable. So any secondary carbocation will reform, if it can become an allylic, a benzylic, or a tertiary carbocation intermediate. Same goes for the primary carbocation intermediate. If it can form if it can become an allylic, a benzylic, a tertiary, or a secondary carbocation intermediate, it will change itself to become any one of them, right? If it can, right? And then lastly, we have the methyl. The methyl basically will just change. It will change into anything above, including primary carbocation, because it's the most unstable, right? Because methyl, anything is more stable than a methyl carbocation intermediate. So it will change itself to become anything but itself, right? Ironically. Now, before we finish, let's try an example to illustrate what I mean by the carbocation will keep changing until it reaches a more stable form. Right, let's assume that we have a compound like this. Right, so this is just a carbon ring, call it, okay, attached to a carbon atom, double bond with another carbon, right? And we're reacting this with HBr, right? This is a halide acid, the halide being bromine, right? The acid being hydrogen, right? Now, what this will first become, as we talked about, it will follow the Markovnikov Rule, right? So the halide acid will undergo cleavage, becomes, so the first step is HBr becomes H plus and a Br minus, right? Giving us a halogen and a hydrogen positive ion, which is acting as a electrophile, right? And step 2, this electrophile will attack the double bond, right? And then forming 2 possible carbocation intermediate, right? So the first one is, so A would be most of the electron will go to the right hand side of the right carbon will go to the carbon on the right hand side of the double bond, right? So this become more negative and this become more positive, right? Relatively. Second, the other possible outcome, intermediate outcome, would be that after the bond is broken, most of the electron will go to the carbon on the left hand side, making that more negative and making the right hand carbon more positive, right? Now, hopefully by now, Chantelle, you will know that if option A were to take place, the hydrogen will attach here, right? Making the compound become, well, making the intermediate compound becomes a, oh, hold on, this should be H2. I forgot. H2. So now become H3. Yeah. Now making this one a secondary carbocation intermediate, because it got one group, one carbon group, and one carbon group, like got two carbon group attached to it, right? So it's a secondary carbocation intermediate, right? And this, and if part B were to, option B were to take place, it will form a H will attach here, right? The H positive will attach there, and it will form hold on, am I missing something? Of course, I'm missing a H. There should be two H here. So it should be a H there. My bad, silly. So when the H attached there will be H2 here, making this more positive. Yeah. So now, if option B were to take place, then we will have a primary carbocation intermediate, because only one carbon group. Now this one does not count, right? Because this whole thing is one whole carbon group. So you can't say there's two carbon group here, but because we're treating it as one, right? So this is a first, a primary carbocation intermediate. Obviously, it is less stable. So this one will break down again and forming, 50-50 secondary and primary carbocation intermediates again. So obviously, this one will be the majority, right? Eventually, it will become all secondary carbocation intermediates. But does it stop there, right? Does it stop there? Because, think about it. So let's go down a bit. Now, knowing that this is our dominant intermediate, so pause here, and then CH3. Now, can this, since this is secondary already, now can it become more stable? All right. Now, we know that the allylic and benzylic is more stable than the secondary carbocation intermediates, but there's no double bond around anymore, right? Or the only double bond is broken down, so you can't form any of that. So there's no way you can become a, well, so far that I know, maybe I'm wrong, but allylic and benzylic would not be an option. At least benzylic wouldn't be an option here. There's no benzene here, right? So that wouldn't be an option. Now, the thing is, can it become a tertiary carbocation intermediate? Now, how does it change again is the mechanism behind that is, as long as there is a hydrogen or like a hydrogen right next to this carbocation intermediate, then this hydrogen can come in here and take place or attach to this carbon instead of the hydrogen can come in here, attach or bond with the carbocation instead, right? So this will either become this, making this more positive, because it lost an electron, or it lost a hydrogen, or back to B, right? There's no, sorry, not this one. We can go back to this form, right? So we can also take one hydrogen here, attach it here, and make this more positive. But no point doing that because we know it is more unstable that way. So the system will not go that way because it requires more energy. So, but would the system go this way? Now think about it. Of course, right? Because right now, if it happens like this particular carbocation intermediate here is a what? It's a tertiary carbocation intermediate. Think about it. It's got one R group here, one R group here, and one R group here, right? So I should mention that all this little corner represent a particular group, now a carbon group, right? It's like that. At least a carbon group. So they are all C's here. Could be more attached to it, but at least a C. So right now, this particular carbocation intermediate is a tertiary carbocation intermediate, which means it is more stable than previously, which is a secondary. So the reaction will favor. This reaction is favored, so it will become this eventually. So that's what I meant by, if the carbocation can change itself to become more stable, it will. The system will allow it to do it, or the system wants it to do it, right? Because it is more stable, require less energy. So this is one very good example to show you that this could happen. Now, I would not trouble you with any more of my talk. By now you probably should be very tired, right? But everything comes with a price, Chantelle. I know you might be tired after all this, but now you learned more, right? Now it makes more sense of why the Markovnikov rule happens that way, and the reason behind the mechanism behind it, and you learn something more about intermediates, especially carbocation intermediates in this case. So hopefully you learned something, and hopefully things become more clear to you. And you know, teachers always say, oh, you should find, people always say you should find more, you should enjoy your work more, or your study more, which is very difficult to do if you don't understand it. Now, hopefully after watching this video, you understand it more and you can enjoy it more. All right. Now this time is really the end. Now, don't wait for it. All right. just close the video after I say goodbye. Goodbye.